So yeah, today we are going to talk about another type of the generative models, which is about the flow matching the model. And probably not for today, but the Wednesday, we're also going to see like why we are discussing this kind of like new generative model and how this is also kind of like related to diffusion model. And also what are the kind of the advantages of like having this kind of the flow matching the model. So previously, we basically discussed some kind of the pros and the cons of the diffusion model in terms of the diffusion model is kind of good, that can basically produce very high quality the samples, also with some kind of the large the diversity, and also the training is also very easy, so basically also very easy to implement as well, and also can be applied to the many applications as well. So we also discussed many kind of the types of the guided the generation the process. One of the kind of the biggest downside of the diffusion model is that it basically involves lots of some kind of the iterative the process that basically makes the computation very slow. So here the discussion last time was that how we can basically make the generation the process the faster in terms of like reducing the number of the steps. So the basic idea for that is that we first started to see basically how the SDE formulation that we have seen for the diffusion models are also related to the ODE as well. So basically what we could see is that both for the forward process and the reverse process, we could see that those kind of the formulation that we have seen for the DDPM and also the DDIM case can be basically converted into the SDE in the continuous domain. And also each of the SDE also could be basically converted into the corresponding the ODE, is some kind of some converting basically the formulation. So the problem becomes that now we can run the generation the process as kind of solving the corresponding the ODE the formulation. So basically the question is that how we can also accelerate the ODE solving the ODE formulation using some kind of dedicated the solver for the ODE formulation that we are seeing. So we didn't see some kind of details in terms of like how we can really convert some of the stochastic differential equation into the ordinary differential equation. But the basic idea behind this kind of conversion from the SDE to the ODE is basically based on the equation, which is called the Fokker-Planck the equation, which is basically describing how we can find a ODE, which is basically having the same the marginal distribution at each of the time step t. So based on this formulation and also the SDE formulation that we know for the diffusion of the process, we can basically derive the ODE formulation that we have seen last time, which was the probability flow of the ODE that we have seen last time. So given the ODE formulation here, the question is that we could consider using some kind of any numerical solver for the ODE. But the downside of like using the numerical solver is that we also require to basically run the multiple steps to get some kind of the very accurate outputs. So the question is that how we can basically derive some kind of the dedicated solver for the specific the ODE formulation that we have here in terms of that we can get some kind of the accurate outputs by just running the few steps of basically the computation. So by basically deriving that specific solver, what we could say is that only with some kind of the 10 steps or less than the 10 steps, we could already get some kind of the results which is like more realistic compared to like running the DDIM or DDPM, the multiple steps. So this was the basic idea in terms of that we are seeing like all the formulation in the continuous space and also seeing basically the ODE formulation describing the everything and basically making some kind of the dedicated solver for that specific ODE formulation in terms of that we can basically compute the formulation with some kind of the few number of the steps. So in this context, we are also going to see some kind of the different type of digital model, which is the flow-based model. So flow-based model is not directly related to the diffusion models, but we are going to see how these are kind of like similar to each other. So there we're going to see some kind of connections between these two. But actually the thing is that flow-based model has been introduced even before the diffusion models. So actually the first time that the flow-based model was introduced was like 2014, like 10 years ago. So it's kind of like relatively like older model than the diffusion models. And the basic idea of the flow-based model is basically not using some kind of the diffusion process, but as we also discussed previously, like all the general model is like all about basically, find some kind of the mapping between some kind of the reference, the distribution, like some kind of base distribution, which is typically the unique Gaussian distribution, into the data distribution. And the basic idea for the flow-based model is that we are finding some kind of the directing some mapping function between these two. And typically also this kind of the mapping function is represented as kind of a combination of the multiple the transformation the functions, which are also invertible. So basically here the question is that how we can find such kind of a series of the invertible functions that can map some kind of the base distribution into our data distribution. So, and also basically these kind of the transformations are also parameterized into the ODE. So in that sense, we are also going to see how the ODE formulations are basically they come into this kind of the new types of generative models. And the flow-based model also has some kind of the lots of the literature. So we won't be able to discuss like all the details for the flow-based models. Obviously, if we want to discuss everything for this, we will need to have another class for those things. So there are lots of the kind of the papers and like many things. So we are not gonna discuss like all the details for that, but we're gonna see like some kind of the some high level the ideas. We are also not gonna get into all the details for the math, but you're going to see like some kind of high level the ideas and how these are also related to the diffusion models as well. So since we are basically skipping some of the details for the today's lecture, so if you are also interested in some like more details, so basically the today's lecture is based on this tutorial in this website. So I strongly recommend you to basically check out this website and basically see more the details there. And also you can also check out more details in the reference the papers here. Lots of kind of the papers here. So before we start to discuss the flow-based model, like one important thing is that we are going to slightly change the notations. So in the diffusion models, basically we considered some kind of the some diffusion the process in the time domain, which is basically decreasing from the t to 0. So the generative process was the reverse process, so rewinding basically in the time domain, starting from the time t to 0. So basically what we could see is that the x0 indicated the sample from the data distribution. And x capital T was the sample from the base distribution, which is typically the standard normal distribution, right? So the generation the process goes from the capital T to 0. And we are going to switch this notation into basically having the generative process from the 0 to 1. So basically, this is the convention that is typically used for the flow-based models. So we will see that now here the x1 means basically a sample from the hourly data distribution, basically the data that we are using for the training, and x0 is basically sample from the base distribution, like basically coming from the standard normal distributions. So please keep this in mind. So we are changing the notations that is also making all the kind of things to be more complicated to basically understand. So that's basically the basic idea. So we are going to basically start with the normalizing flow. So let's say some kind of like very basic idea for the normalizing flow. So basically here what we are going to do is that we are going to find a kind of the direct mapping between the reference distribution to the data distribution. So let's say this pi indicates basically that function, the mapping from the base distribution to the data distribution, which is basically continuously differentiable function. And also its inverse function also exists. And also that inverse function is also continuously differentiable. So let's think about like having this kind of function. And we're also going to see like how we can find such kind of function. So then given some kind of the reference distribution like the P0 here, so we are starting to use some kind of the change the notation here, right? So P0 is now the reference distribution, which is the typically standard the normal distribution. From that, we are basically also going to define the distribution like P1, which is basically a distribution induced by following the sampling the procedure. And the procedure basically is that we are sampling from the given the reference distribution and mapping this sample into the another basically sample here. So let's say this is kind of the sampling the procedure, and this will basically transform the given the reference distribution into the another the probability distribution, right? So let's say this is kind of like our sampling the procedure here. And given this kind of the relationship between the P0 and the P1, what we are going to see is that we are going to see some kind of two properties. The first property is that the probability mass in the original space, in the space of the P0, should be equal to the probability mass in the transformed space in the X1. So basically, this relationship holds like this. So this is basically showing some kind of the equality between the two probability mass, which is like the probability here multiplied by the some kind of the infinitesimal amount of the x0 and the x0, x1 and x0 here, right? And given this, also what we are going to see is that so now the x0 also can be mapped from the x1 by the inverse mapping here, right? Then the absolute value of the Jacobian the determinant, this term, is basically measures the local scaling of the volume. So when you think about that, we are having some kind of the infinitesimal the volume for the x0 and the x1. The scaling, basically the infinitesimal the volume of the x1 to the x0 is basically represented by this like absolute value of the Jacobian the determinant here. So this is basically deciding some kind of scaling factor between these two. So when you combine these two, like what we can basically see is that now we can directly derive the probability distribution for the P1 as like this. So given some kind of the reference distribution like P0, and also the some kind of the mapping function pi here, which is typically called the flow map. So given the P0 and the pi, now we can derive some kind of the the analytic form of the probability distribution of the P1 in this way. In a way that when you basically compute some kind of inverse function of the pi like this, and also it's the determinant and also the Jacobian like this. The same function also can be represented into the log scale like this. Then we are basically having some kind of the plus here, the same formulation. So we are going to call this kind of process like mapping the P0 to P1 through the mapping function pi as kind of the push forward the operation. So when you basically define the pi as kind of the some kind of the mapping function from the P0 to the P1, now we are saying that this is kind of the push forward the operator, which is basically mapping like the P0 like this. So what we can basically see is that when you see this kind of the notation, basically this means that now we can sample from the P1 the distribution here in terms of that we are sampling from the P0 first and mapping to the pi. So that's basically the pushing the P0 distribution to the P1 kind of distribution. Make sense? So given this kind of the notation, and also basically how we can derive some kind of the P1 distribution here, using some kind of Jacobian determinant here, let's quickly see how we can transform a kind of the Gaussian distribution. So let's think about that we are having this kind of like 1D Gaussian distribution, which is the base distribution like this. And we want to basically push this P0 distribution into another the P1 distribution through this kind of the affine transformation. And when you basically like when the A is not zero, we can also derive some kind of the inverse mapping like this, right? So given this kind of the reference distribution, and also basically the flow map, like pushing the P0 to the another the distribution like P1, can you derive some kind of the analytic form of the P1 using these two? So let's quickly try this out. We can quickly see that like the absolute value of the Jacobian the determinant becomes like simply like 1 over A for the 1D affine function, right? So if we basically multiply this, and we can rewrite the distribution like this. And when you multiply A here, both for the denominator and denominator here, then we basically get some kind of the another Gaussian distribution like this. This becomes like applying this kind of the affine transformation into the mean here, and also multiplying the square root of the scaling term A here into the variance. And this output is also consistent with some kind of the linearity, the condition, the property of the Gaussian distribution that we could see before. That makes sense. So we can say that given this kind of the flow map, the mapping from the one distribution to the another distribution, the pi here, and and also given some kind of the base distribution, we can basically induce the another distribution based on this kind of the push-pull the operation. So this was kind of like the simple example that we are basically pushing like one Gaussian distribution into the another the Gaussian distribution through the affine transformation. Makes sense. So basically what we can say is that while there are like tons of the details, like one thing we can quickly try to do is basically finding such kind of a function pi given the samples of the unknown the data distribution. So given some kind of the base distribution, then we are going to typically choose the standard, the normal distribution, and also the samples from the unknown the data distribution. If we can find such kind of function pi, which is basically mapping the samples from the base distribution into data distribution, then that becomes our the model, right? We can basically do some sampling from the base distribution and basically do some kind of mapping through that. So here the question is how we can find such kind of the function pi here. And there are lots of details in terms of how we can calculate this loss function. But here, basically, one of the also the key thing is that how we can basically also find such kind of the invertible function. So basically, if we go back to the push-forward operator, what we can see is that the push-forward operator is basically involving the computing the inverse of that the mapping function, right? And also the computing the Jacobian and also the determinant of the Jacobian as well, right? So how we can basically find such kind of the invertible function and also computing the inverse itself is kind of the one challenge, the part. And also how we can efficiently compute the Jacobian is also another the challenge. So basically based on that, so what we are also going to do is that now we are going to consider representing such kind of the mapping function as kind of a sequence of the functions. Let's say, so we are having some kind of the p number of some kind of functions, and each of the kind of the function here is kind of like represented into this kind of like simple form. In terms of that, we are basically adding some kind of the offset to the given the data point xt here. So by basically having this kind of the simple form of the function, while basically making some kind of composition of those functions, we can basically consider easily computing all the inverse and also the Jacobian as well. So this is like the basic idea that we are basically having some kind of the discrete samples in the time domain, and for each of the interval in the time domain, we are defining this kind of mapping function. That sounds already quite similar with some kind of recursive VAE kind of process, right? And also diffusion models. And what we are also going to do, like going one step further, is basically not even like dividing the time domain into some kind of specific number of these steps. We are also going to think about this into in the continuous time domain, in terms of actually making the delta t here to get closer to the zero. So basically, when you have this kind of the function, which is like defined with some kind of the residual the update term here, you can see that this is basically given the xt, we are basically adding this term multiplied by the delta t here, right? Adding this kind of the residual into some kind of input xt here. And if we consider basically having this kind of the steps like infinite times, then we can see that actually this kind of the residual becomes some kind of the velocity term here. So basically when we take the derivative of the xt with respect to the time basically t here, we are getting this kind of the velocity term here, which basically means that we are basically getting another kind of the ODE formulation, the simplest form of the ODE. So given this kind of the ODE formulation, now we can basically sample the xt by calculating all the things. So starting from the x0, basically when you calculate the ODE formulation, now we can basically compute the xt like this. So given this kind of the velocity basically field or the vector field here, we can basically sample the xt by solving this kind of the equation. So here basically what we are also going to see is that given this kind of the velocity field, the vector field here, we are also going to see how we can calculate the derivatives of the probability distribution. So given the Fokker-Planck, the equation that we have seen in the previous slide, what we can see is that we can derive some kind of the relationship between the vector field here and also the derivatives of the probability distribution like this. So can you quickly like derive like how we can, given this kind of the ODE formulation, how we can also compute the derivatives of the probability the distribution like this? This is actually a very simple question. Any ideas? So actually the answer for this is like quite simple. Like, this is really showing the connection between the SDE and the ODE here. But actually the formulation that we are seeing is kind of a special case when the basically the G function here is basically zero. So when the input is the ODE, then we can basically consider basically canceling this out. Then we could see that actually we can derive the derivatives of the probability distribution here with some kind of divergence of like this, the multiplication like these two. So this is basically the equation which is showing the relationship between the vector field, basically define some kind of the mapping through some kind of the distributions, and also the distribution itself for every time step t. So given the flow of the probability distribution of the PT here, we can basically find some kind of corresponding the vector field here. Or in the other way around, given some kind of the vector field, we can also derive some kind of the probability flow, the distribution of the flow like the PT here. So this is basically showing the connection between the flow of the probability distribution and also the vector field itself in the space. Makes sense. So given this, like after some kind of the long derivation, what we can also see is that we can also compute the log of the probability of each of the sample of the x1 here as well, by also solving the another the ODE like this. So basically we can compute, like we can not only sample the x1 here, we can also basically compute the probability for each of the sample of the x1 here. And based on this, what we can consider is that now, instead of like finding some kind of the mapping function, the flow map from the P0 to the P1, now we can consider learning some kind of the vector field, which is also mapping the P0 to P1. So it's basically a matter of like whether we are representing the mapping through some kind of the direct the mapping function or some kind of the vector field, basically, which is represented like this. So there are also lots of some kind of the details in terms of like how we can really learn this kind of the vector fields. But basically, like all the challenges like learning this kind of vector field is that it's also involving solve this kind of the ODE formulation. So every time like when you compute some kind of the log the probability of each of the sample the x1 here, we need to solve the ODE formulation. That is taking tons of time in the training. So that's basically kind of the bottleneck in terms of like how we can learn this kind of the vector field that can be also be another representation of our degenerate model. So this is kind of like the point like where we are basically thinking about some kind of the new idea, which is the conditional the flow matching. So this is kind of like the main idea that we are also going to see. So here the basic idea is that let's first assume that we already know such kind of the vector field satisfying this. Basically, this means that we already know the vector field, which can basically map the base distribution P0 to the data distribution P1. Here, basically, one quick question is that, is there such kind of the vector field unique or not? Any guess? So given any kind of the two probability distributions, if we consider having some kind of the vector field mapping one to the other, would there be some kind of the unique vector field or multiple vector field? Yeah, actually, obviously the answer is no. I mean, there can be, so the vector field is basically representing the flow from each of the point in the P0 distribution to each of the point in the P1 distribution. And that there can be lots of the way that we can draw this kind of the trajectory between these 2 points. And also the correspondences, they can be basically changed, right? So there can be multiple ways to make this kind of the vector field. But basically what we are interested in is that we are interested like only one vector field that can like basically show any kind of the mapping from the one to the other. So given any the vector field that's basically mapping the P0 to P1, we can consider basically training a neural network, which is basically giving some kind of the vector field information like this, which is basically regressing the given the vector field like this. Then our neural network will basically play the role as kind of like, showing the mapping from the P0 to P1, then that can be used for the generative process, right? And by the way, isn't this kind of like equation similar with like what we have seen before? Like directly regressing some kind of the quantity for each of the some kind of latent the data point xt. You can see that there are some kind of some analogy to some kind of things that we have seen in the diffusion models, right? So the loss function is already kind of something that looks kind of similar with the noise prediction network in terms of that we are basically getting some kind of the quantity in some kind of the intermediate data point xt and basically regressing that quantity and that becomes our the loss function, right? So that's kind of the point that looks kind of similar with the diffusion models. But here the question is that, so now we are assuming that this kind of the vector field is already given. And we try to learn those kind of things using the neural network, right? But if we already like knew this kind of the vector field, actually there's no point to learn this, right? It's basically the problem is like solved. We can directly use basically the given the vector field for the generation of the process. So here the question is that, so do we know this kind of the vector field? No, actually, that's kind of a problem. So that's why we want to learn this kind of the vector field. So without knowing this kind of the vector field, how can we minimize the objective function? So that's kind of the point. So we are going to discuss some kind of the interesting the idea, which is basically allowing us to basically learn this kind of vector field without having some kind of the ground truth vector field. So for that, we are going to see some kind of the conditional probability distribution. So let's think about like this conditional the probability distribution of the p xt given the x1. So since we changed the notation, here the x1 is basically the data point, given the data, with samples from the data distribution, and the xt is some kind of intermediate data point, right? So this is basically a probability distribution of the xt given some kind of data point x1. And we are going to consider any kind of the conditional probability distribution, which is basically satisfying like these two constraints. So when the t is equal to 0, then it becomes like the following some kind of the given the base distribution, whatever x1 we have. So whatever x1 we have, like if t goes to 0, then the conditional distribution becomes the base distribution like this. And if t goes to 1, then it becomes like almost the same with the Dirac delta the function. That the mean becomes the x1, and it becomes like very picky, some kind of the distribution like this. So can you basically like visualize such kind of the conditional the probability distribution? So in the one-dimensional case, it will look like this. For each of the x1 here, as the t goes to 0, the samples basically follow the given the base distribution. And as t goes to 1, then it is basically like, concentrated on the given the x1 like this. So this is kind of the visualization of the conditional the probability distribution. Makes sense? And also, by the way, so is this kind of the conditional distribution also similar with like what we have seen before? Is basically sampling the xt given some kind of the data point x1, right? Actually, this is kind of the same with the forward jump distribution that we have seen in the diffusion model. So in the notation of the diffusion models, the x0 was the data point. And this was basically distribution, basically, the probability of the xt given the data point x0 here, right? So basically, these two are the identical things. So we are now seeing some kind of the forward jump distribution in the diffusion models in the context of the flow-based model. Make sense? So also given the P0 and the P1, given the base distribution and the data distribution, there can be multiple like the conditional the probability the distribution, the the xt given the x1. So we can basically choose anything as as we have done so far. Like we are also like basically working on some kind of the Gaussian distribution, right? So we are also going to basically consider a kind of the family of the Gaussian distributions that looks like this as kind of the conditional the probability the passes mapping the P0 to P1. So we are basically having some kind of the function of the mean here and also the function of the variance here. In a way that we are defining this like the mean and the variance in a way that when the t goes to 0, then it becomes the like 0 and the 1. This becomes the unique Gaussian distribution, right? And if t goes to 1, and then we are basically having some kind of the Dirac delta distribution like this. So basically, we can make any kind of the mean function and the variance function that satisfies basically this. I mean, it doesn't need to be like this specific form of the conditional distribution, but for the simplicity, we are going to consider like this specific form. Okay. And given this kind of the conditional probability distribution, now we can also consider the conditional vector field. So in the previous slide, we have seen that like given any kind of some flow of the probability distribution, we could consider some kind of the corresponding the flow map here, right? The vector field. And also for the conditional, the flow of the conditional the probability distribution here, we can also consider some kind of corresponding the vector field. The conditional vector field represented in this form. If it's coming from the same equation. So here basically one more thing that we are going to see is that given some kind of the conditional the vector field is and also the conditional the probability the path is the conditional vector field unique? The answer is also no. There can be also the infinite the number of the conditional vector field given the conditional the probability distribution. Which means that there are basically like all the options, both for the conditional the probability the path and also for the conditional the vector fields as well. So among the last of the options, we are going to consider this specific combination, but it doesn't need to be this specific combination. The only reason that why we are basically considering like those options is that because like these are all based on the Gaussian distributions, which basically make our life like much easier, like everything becomes like much simpler, right? So let's think about that. We are having some kind of the conditional the probability path, which is like defined into this specific the Gaussian form. And given this like mean function and also the variance function, now we are also going to consider the flow map, which is like deriving to this form. And also the corresponding vector field, while there can be also multiple vector fields, we are going to consider this specific vector field that looks like this. So these are basically our some kind of the choice for the conditional the probability path and the conditional the flow map and also the conditional the vector field. Makes sense. So here also like one thing is that given this kind of flow map, what we can do. So this like flow map is basically the mapping from the given the base distribution to this specific the conditional distribution. So as we have seen in the previous slide about the push-pull operator, if we want to sample from this specific conditional distribution, what we can do is that we can consider like this like flow map is like defining the push-pull operator like this, which means that now we can sample from the P0 first from the base distribution and push this sample into the space of the conditional distribution by mapping through this like given the function. So this is basically the meaning of the flow map here, which is basically pushing the P0 distribution into the conditional distribution given the x1 here, into the pxt distribution like this. And as we have seen in the previous slide, we are specifically considering this flow map, mapping the x1 to the xt like this. Make sense? So given this, like you might think about like why we are thinking about like caring about the conditional the probability path and also the conditional the vector field. So we are going to see like why we care about this. So the first reason for that is that now we can also calculate the marginal vector field, this one, based on the conditional vector field into this formulation. So we are basically seeing some kind of the connection with the marginal vector field. That was something that we really wanted to get with some kind of the conditional vector field that we defined based on some specific form of the conditional the probability path, right? So we are not going to see some kind of the details, so like how we can exactly prove this. But basically, we are going to quickly see like how we can verify this based on those formulations. So we are going to see that this equation, which is coming from the Fokker-Planck the equation, can be rewritten based on these two equations. So the first one is coming from also the Fokker-Planck the equation, for the conditional the vector field, and the second one is basically coming from this statement, right? So given these two, basically what you can see is that if we plug this into this equation, this is nothing but the marginalization, like replacing this term into the divergence of like these two multiplication, and also dividing the pxt and also multiplying the pxt again here. And based on that, we can see that the equation that comes from the Fokker-Planck the equation actually can be derived from these two equations. So this is like giving some kind of the sense of like how this kind of the statement can be basically proved, right? And the more important thing this is that actually this was the loss function that we wanted to compute, right? The problem was that we don't have the information about the vector field, the marginal vector field here. But based on the facts that we have seen in the previous slide, what we can actually see is that this loss function is actually equivalent with this loss function, which is basically defined with the conditional vector field like this. So this is like the key fact. So without basically having some kind of the marginal vector field here, if we can calculate the conditional vector field here, then we can replace this loss function into the another loss function in a way that now we can train some kind of the neural network that is basically learning some kind of the vector field based on the conditional vector field. So that's basically the whole idea. So we are also not going to see some kind of the details in terms of how we can exactly prove this. But basically what we are going to see is that we are going to say that the expectation of like this kind of the two dot product is the same based on this equation. So if we basically see some kind of details, like we can say that this expected value can be converted into like taking the interval of the pxt here, while replacing the marginal vector fields like this. And if we rewrite all the things, then we can say that actually this expectation value, the expected value becomes the same with this expected value. So from this, like what we can see is that like the training, the flow, the matching the network can be basically, basically trains is the same as like training with this loss function by replacing this part into the conditional vector field. And given the choice of the conditional the probability distribution, we could see that how we can derive this term, right? So this is kind of like important part in terms of that. While we don't know the marginal the vector field, now we can compute the conditional the vector field depending on our the choice of this specific the probability the distribution. Make sense? And here, one more thing is that basically how we can sample from this. So this is basically expected value for the sample of the x1. Basically, the x1 is basically given some kind of data points, right? And given the x1, we also need to sample the xt as well. So how can you sample from this? We have seen this in the previous slide, right? So for the vector field, if you also know some kind of the corresponding the conditional the flow map, which was defined in this way in the previous slide, right? So if we have this kind of like the conditional the flow map, this function. So this is basically the mapping function from the P0 to this specific the conditional the distribution, right? The pxt given the x1. So we can basically do some kind of the push forward operation in terms of the we first sample from the x0, p0 like this, which will come to x0 here, and mapping this to the xt. So sampling from the xt given the x1 actually becomes like we are sampling both the x1 and the x0. And based on that, we are push forward the x0 into the xt space, and then calculating the conditional vector field conditioned by the x1. And this becomes our the final loss function to train the flow matching the model. So you can see that some kind of the difference with the diffusion model is that in the diffusion model, we only care about some kind of the data points. So from the data points, we do some kind of the forward jump and basically minimize some kind of the noise, right? With this predictive noise and the noise that we added for the flow jump. And here some kind of difference is that we sample not only the x1, but also the x0 as well. And based on the x0, we basically sample the xt that becomes some kind of push forward operation. And then based on the given the x1, we compute the conditional vector field here. And we basically minimize the regress the given the vector field using the neural network. So that becomes some kind of difference with some kind of diffusion models. Makes sense? So if we go back to some kind of a previous slide, what we wanted to see was that there can be multiple ways that you can define some kind of the conditional probability passes here. We are specifically considering this specific deform using the Gaussian distribution. And for that, we are also specifically considering this flow map and also this vector field, right? And given this combination of the probability, the conditional probability pass, and also the conditional flow map, and also the conditional vector field, what we could do was that we could first basically convert the loss function into this form in terms of the now we are calculating the conditional the vector field here. And we also sampled the xt here using the flow map by applying some kind of the push forward operation, sampling from the p0 and pushing into the pt space, right? That becomes kind of the way that we are basically training our kind of the flow matching model for this specific the network. So we discussed some kind of the general form of this specific the family of the conditional probability paths, and we could consider any kind of the function for the mean and the variance if they satisfy like these constraints, right? And what would be some kind of the examples that basically satisfy like those kind of the constraints? Any ideas for the mean function and the variance function here? So as I like mentioned in the previous slide, actually this conditional distribution is nothing but that we have seen before. This is the forward jump the distribution. And as we have discussed in the previous lectures, actually the diffusion models are also defined based on our definition for the forward jump distribution, right? So we discussed the two types of the diffusion models. Like one is the variance preserving the form of the like the DDPM, and the other one was basically the variance the exploding the diffusion model. And each of these were basically was also defined with some kind of the specific the choice of the forward jump distribution, which means that we can consider using this specific deform in our flow matching model as well, if they satisfy these all the constraints. Actually, they do satisfy those constraints, so we can really consider using the same the forward jump distribution as kind of our definition of the conditional probability path, and then we are deriving the flow map and also the conditional vector field as well. Make sense? So this becomes like we are using the same definition of the fourth jump distribution, but using different equation, different loss function to learn the mapping. So let's think about the case that like we are using the variance preserving case. So by the way, also notice that we are having the 1 minus t here because we are now changing the flipping the t notation. So the generation, the process goes from the 0 to 1, not to the t to 0, right? So because of that, now we're having the 1 minus t here. So in the variance preserving case, the fourth jump distribution was defined in this way. And based on that, can you also derive some the conditional the vector field given this kind of the definition of the conditional the probability depends? So we can basically use this equation here. So let's quickly try this. So by the way, this is basically the derivative of the function sigma function here with respect to the time t here. So when you see the basically sigma t here, actually this basically means that this is the function sigma with respect to the t as well. So this is like the function of the both the x1 and the t. Did everyone get this result? So by taking the derivative of the mean and the variance function here, we can rewrite all the things. Then we can simplify the this conditional vector field into this form. So you can see that basically based on the fourth jump distribution, the definition of the fourth jump distribution for the DDPMD formulation, we can derive the conditional vector field. And based on that, now we can consider not running diffusion model, but the flow matching model for the same the type of the fourth jump distribution. So as we also have discussed like multiple the four jump distribution, that is also giving some kind of the different the types of the diffusion model. We can also consider like using different the conditional the probability test in this case, right? So let me leave this as some kind of the homework that you can just try yourself after the lecture. But also the good thing of the flow matching the model is that we have some more the flexibility in terms of like choosing the conditional the probability distribution here. So also in the diffusion model, we could consider like various the types of the function, the jump distribution. But now we're having some more the flexibility in terms of the even we can choose this kind of like the simpler form of the conditional distribution in this way. So this is like typically used for the flow matching model. And for this specific the conditional distribution, the probability pass, if we derive the conditional vector field, then the output also looks like this. And now we can consider like using this kind of combination, but it doesn't need to be this specific form, but we can consider using some kind of the different combinations. But this is like one of the simplest the combination of the conditional the probability pass and also the flow map and also the vector field that also becomes some kind of the simple, some kind of linear function. So given this kind of combination, now we can consider basically calculating the conditional vector field, minimizing the loss, while basically sampling the xt through the push forward the operation. So that will be something that you will need to implement in the assignment 7. And the good thing of like training this kind of the flow matching model compared to the diffusion model is that now we can get some kind of the more like the straight the trajectory in the space, which means that like when you think of like having some kind of the trajectory from the like one point in the P0 space from the P0 distribution to the other point in the P1 distribution, there will be the more chances to get some kind of a straight the trajectory, which means that in terms of like solving the ODE, even with the fewer the number of the steps, there is like higher chance to get some more accurate the outputs. So that's the kind of the power of like having some the full DMX model in terms of that we can reduce the number of the computation by basically having some more the straight the trajectories in the space. So if we compare some kind of the output of the training between the diffusion model and the flow matching model. So these are the cases that we are using the diffusion deformulation, the diffusion, the fold jump distribution, and training that using the diffusion model. And we are seeing this kind of the output. And this is also the case that we are using the same the conditional the probability test, but now training with the flow matching. And now we are even using like the simpler the form of the conditional the probability test and training that as kind of the flow matching. And you can see that this basically means the number of the function evaluation, the number of the steps in basically solving the ODE. And you can see that even only with the full the number of the steps, you can see that we are already getting some kind of the distribution, which is quite close to the given the data distribution. So this is kind of the power of like using the full dimension model, which basically gives some kind of the more the accurate the generation the outputs with some kind of the more the fewer number of the kind of these steps. So this is kind of the basic idea to the flow matching. And on the next the Wednesday, we are also going to see how it's more the higher level the idea in terms of the how basically the flow matching the idea is also transforming the field of the generative AI the field in terms of like basically making it much faster the generative models. So do you have any questions for the flow matching? So this coming Wednesday, we are going to continue the discussion for the flow matching, kind of some kind of higher level the ideas. And we are also going to have the session for the last assignment, assignment 7. And then there will be some kind of the discussion for for those kind of things. And then next Monday, we are also going to discuss some kind of the future of the generative models. Okay, so if you have any questions for the flow matching, please leave the questions on this lab. And I will see you next Wednesday. Thank you. Bye.